So welcome everybody. Welcome to the IoT Plus Coffee Break on Smart Grid today. We are going to have two experts who will share with us their knowledge in the energy sector. But first of all, I will introduce myself. Hello, my name is Jonás. I'm the network manager of IoT Plus Network. And I will be the moderator today with the support of my colleague, Jackie, who is behind the curtain, taking care of the technical part. And before I start, so a couple of words about the IoT Plus Coffee Break, the organizer of this event. The IoT Plus Network is an association of IoT actors commissioned by the BMWK to exchange the IoT ecosystem in Germany. We belong to the German initiative, the Hub of Innovation and Digitalization. And with cross-sector collaboration, we promote tech companies and foster their potential, creating the best possible synergies for companies, startups, and research. So now let's introduce our two speakers. The first one will be Ivan Gankevich, product lead at Staex with a background in distributed system research. Staex is one of our members, and they are doing an incredible job working on IoT infrastructures. In this case, Ivan will show us how Staex improves smart grid IT infrastructure, reducing data usage and costs up to 20 times. Then will come our second speaker, Martin Asman. He is a researcher at Bergische Universität in Wuppertal, electrical engineer with a master's degree in electrical engineering, pursuing currently the PhD degree at the same university in Wuppertal. So he will share with us his research work on a smart grid forecast called multi-agent based grid state forecast for peer-to-peer energy and flexibility markets. And then how we proceed today. So our speaker will have a 10 minutes presentation where they will talk about the topics, followed by a 10 minutes Q&A, where you can ask your questions. So please, if you have any question, raise your hand or wait in the chat, and then Jackie will unmute you, and you will be able to ask your question. So now everything's set. Let's start with our first presentation with the first speaker. So Ivan, you can start. The floor is yours.
Thank you, Jonás. Let me share my screen. And I hope you can see my presentation. Hello, my name is Ivan, and my presentation is about VPNs designed for smart grids or not. I will start with a few words about how we see smart grid IT infrastructure. First of all, this infrastructure includes devices or sensors. These sensors are usually connected to IoT gateway, which is basically a router or a computer that runs specific software that can process the data. And this computer or the router connects to the cloud using some sort of mobile network. Usually it's 4G or 5G or some older standards. And usually people use VPNs to protect the data from attackers, because this data is transferred over the internet. And we use a scientific approach to develop our product, and as part of this approach, we do benchmarks. So before releasing the feature, we always do benchmarks to see how we fare across other VPNs and across other competitor products. And our first benchmark was the idle data usage. It is this benchmark measures the amount of data that is transmitted over the network by a VPN that does nothing, basically. So this VPN doesn't transmit business data; it transmits some additional data that is used to maintain this virtual network over the physical one. And as you can see from the results, different VPNs show wildly different data usage, up to 400 megabytes per month for one popular VPN. At the time that we did this benchmark, we didn't know if it's big or not. Are these numbers big or not? Do they matter? So we proceeded with the second benchmark. And the second benchmark was to measure how a typical sensor transmits the data and how much data it transmits per month. We grabbed a few sensors, a smart meter, a smart light bulb, and also GPS receiver, and measured how much data they transmit per month. And as you can see, it is less than 20 megabytes per month. And finally, we did our research on the IoT gateways. Usually, they connect multiple sensors because of the efficiency. Typically, gateways connect around 20 sensors. Some gateways allow to connect 100 sensors, but this is not typical situation. Typical situation is around 20 sensors per gateway. And if we divide the amount of data which is transmitted by VPN per month by the amount of data transmitted by 20 sensors, we see that some VPN transmit as much data as 20 sensors per month. This means that using this VPN for IoT gateway means that this gateway will have twice as much sensors on average. So it's the same cost for the monthly data usage. So this was our first benchmark, and of course we did a lot of others, but this first was the most important one for us because we wanted to reduce costs for our clients who use mobile data and who use specifically GPS receivers to track their devices. And the second benchmark is just a sneak peek. It's benchmark for the overhead. The overhead is the amount of data VPN attaches to each packet that is transmitted over VPN network. So it means every packet that you send from your IoT gateway to your cloud is larger than the usual packet, which is sent without VPN. And this data, of course, accumulates and also leads to much greater data usage. Here we only have this histogram. We didn't measure anything else, so we can see that we have a very small overhead compared to open source VPNs. However, we haven't measured the proprietary VPNs in this benchmark. So how we applied our knowledge? We released a new version of our software, which is a VPN for mobile networks and for IoT devices, and we are close to deploying this new version with our client. And our client manages mobile EV chargers. They install the router inside each charger that monitors the GPS location of this charger and also tunnels the Modbus traffic between the router and their management server, which is in the cloud. And Modbus traffic is notoriously unencrypted. So that's why they use VPN, because there's no way to encrypt this traffic other than use VPN probably. And for them, we provided two-way connectivity for remote maintenance and also encryption for this Modbus traffic. I think it's a good time to stop and answer questions. Thank you.
So, anyone has any question? So, question from the audience? If not, I have a couple of them. So, Ivan, from my experience, sometimes having a light system at the end, as Staex looks like, is because companies make a big effort in the previous phases with complicated installation and configuration. So how about the Staex? How is the configuration and installation phase?
Thank you for the question. We try to make our product as simple as possible to install. This is our goal because we believe that making reliable only simple software can be reliable, and we want our VPN to be reliable and to be secure and to be easy to maintain and to install.
Okay, and then the maintenance and scalability of the system. So how complex is it?
This VPN have you can see the whole status of the whole network from a single node if you want. If you want more fault tolerance, then you can add more central nodes that can be used in place of failed one, and then you can also update them in parallel. So when the one node updates, then you can use another node for your network, and this is all automatic. So you will see the status of the whole network from a single node, and you will be able to make software updates in parallel to the actual functioning of the network.
Great. Any question from the audience?
Even I hope you can understand me. I have a question about other advantage of your technology. Indeed, are there other advantage of your technology? If there is a cost-effective availability of 5G and so on, do people still need your technology? Are there additional advantage? So what is not only compress the information to use less capability of communication, or are there anything else?
Thank you for the question. Yeah, good question. We have a lot of other features. We wanted to show only one in this presentation. Just to name a few, we have end-to-end encryption, and in our network, man-in-the-middle attacks are not possible because the public keys of the node are also addresses in our network. And so if you want to spoof the address, you have to steal a private key from the node. So man-in-the-middle attacks are not possible. We also have implemented partially the zero trust architecture. So our nodes and our networks by default do not trust each other. So they always sign their first packet that they send to another node, and all other packets are encrypted between the nodes, and the payload is encrypted to the receiver node. And also we have we have optimizations for small devices, resource constrained devices. We are able to run our network on the routers with 60 megabytes of memory, for example.
Okay, fine. Thanks.
I see on one of your graphic, like Staex 1.x. So now that distributed system blockchains are getting more important, how do you see the evolution of smart grid infrastructure, and especially on the evolution of Staex itself? I mean, because of the 1.x that you say, like the first version of Staex. So how will we develop it?
Thank you for the question. Our plans is to fully implement zero trust architecture. We want also to make as part of these improvements, we want to make applications first-class citizens of our network, so that you can define ports and nodes that this application use, and close all other ports and restrict all other traffic in the network. So in this probably and hopefully second Staex version, you will have fully locked down network, which will be even more secure than now.
Okay, thank you very much for the answer. So anyone has more question from the audience? If there is no more question, we can go to the second speaker. So Martin Asman, you can start. Martin.
Yeah, thank you.
You can share.
I will share my presentation. Yeah. 1 second. Now you should see my title. Thank you for the introduction, Jonás. My name is Martin Asman. I'm from the University of Wuppertal in Germany. And my topic for today is the multi-agent-based grid state forecast for peer-to-peer energy and flexibility markets. The presentation is divided into 3 sections. At first, I will give a short introduction of the Institute of Power Systems Engineering, then followed up by some basics about peer-to-peer energy and flexibility trading. And in the final section, I will showcase the PEAK use case, where PEAK is the research project I'm currently working in. Let's start with the introduction of the Institute of Professor Staex. The Institute currently employs 50 people. 48 of them are PhD students, so it's a pretty big institute. The PhD students are further divided into 5 research groups, and we have access to one high voltage laboratory too, and a smart grid laboratory too, for research and teaching purposes. The 5 research groups and their topics are listed in this slide. The groups are power systems, structures and planning, operation concepts and sector coupling, smart grids and smart systems, energy markets and flexibility management, as well as condition assessment and asset management. And myself, I'm located in the group smart grids and smart systems, with the research topics like state estimation, decentralized power control, or the grid integration of electromobility and buildings. Because of my research project, I'm also working a lot with the research group Energy Markets and Flexibility Management, and their research topics are smart markets, regional flexibility markets, and grid state forecast, which will hear a lot in my presentation. So we come to the second section, the basics about peer-to-peer energy and flexibility trading. To understand why I talk about this, I will give you a short introduction about the research project PEAK. PEAK stands for Integrated Platform for Peer-to-Peer Energy Trading and Active Grid Management. It is supported by the Federal Ministry for Economic Affairs and Climate, as well as the Projektträger Jülich. And the motivation behind this project is due to the increase of load-intensive consumers and decentralized generation plants. The distribution grids are reaching their limits with regard to voltage band and load capacity of the cables and transformers. So the idea or goal is that with new market concepts, these challenges of the energy transition can be solved locally in a distribution grid level. And the main goal with PEAK is to develop a local energy trading platform in combination with preventive and corrective grid congestion management. And to able to do that, it is necessary to integrate the customers. So in this case, it's called prosumers. And so producers and consumers together into the smart energy supply systems. Only with that, it is possible to develop such a platform. And further, how could the smart energy supply system of the future look like? This is what I want to talk about in this slide. And we need to talk about smart grid, smart market, and smart prosumer, and the interplay between them. The smart grid includes 2 sections, the transmission and distribution section. And with the smart grid, it's able to you are able to monitor the grid capacity in real time and regulate the grid states. The smart market can be seen as area around the smart grid. So to be able to start a smart market, you need a smart grid. So the information about the grid capacity, and then you are able to trade energy quantities and services depending on the grid states, and to start a smart market. And then the final part, the prosumer, if you make the prosumer also smart, so that the prosumer is possible for him to actively trade in the smart market, as firstly energy, but for our project important also grid serving flexibilities. So the prosumer is the connection between the smart market and smart grid to sustain the grid stability. And in the first time of our research project, we searched for approaches how to enable the consideration of grid restrictions on smart markets, and we found 5 different approaches in the literature. And now it was our now we needed to decide which approach we are going to use for the PEAK project. And after long discussions and workshops, we finally to choose the market concept parallel markets. If you want to hear about the other 4 market designs, we can talk about that after my presentation, but to save time, I will talk about the parallel markets. At the market design parallel markets, you don't have just one market, but 2 markets with 2 separate products. One product is the energy and one product is the flexibility. It's similar to the redispatch system, but in a local area, in the distribution grid area. And with the parallel markets, there's the explicit offer and use of flexibility. So the prosumers can trade energy in the energy market from one consumer to one consumer. And in the flexibility market, you can trade flexibility to the grid operator if flexibility is requested and if there's flexibility available. So let's come to the last section, the PEAK use case. In PEAK, we wanted to implement the market design parallel markets with an agent-based concept. So each role of the energy system is now represented by an agent. So we have the grid agent, market agent, and prosumer agent. And the 4th agent is needed to communicate the platform or to communicate the platform interaction. And this is the platform agent. And to explain how the platform should work, I will talk about the 4 phases which are possible in our platform. The first phase is the initial phase. This is the start of the platform. At the start, it is necessary for every agent to register in a platform-wide telephone dictionary and to register at the platform agent. The PEAK project was created in the blockchain hype phase, so we also wanted to implement blockchain in our project, but we didn't choose to make the whole trading over a blockchain, but we use blockchain for identifying the participants of the platform. So you can only register yourself with a verified digital identity. And if you have no such identity, you can't participate in the platform. Now we come to the second phase, the green traffic light phase. The green traffic light phase stands for the grid that is a stable state, so there's no grid congestion. And in the green traffic light phase, the prosumer agents can offer and ask energy at the market agent and further it's an energy market. And the grid agent needs to make a grid state forecast to validate the energy results. So only if the grid agent says, calculates no good conditions, the energy market results are validated and given to the presume agents. If, however, if the grid agent detects a grid violation in the grid state forecast, grid flexibilities are requested from the grid agent to the prosumer agents. And this only for the prosumer agents which are sensitive to the grid congestion. This is done by a sensitivity analysis. And as you can see now, besides the energy market, also the flexibility market is opened, where the prosumer agents can offer flexibility to the market. In the red light phase, the grid congestion couldn't be prevented by the flexibility market. So now it's necessary for the grid agent to operate in real time and solve the grid congestion. And this can be done in two ways. The first possibility is through agent communication over the platform. And if that's not possible, it's also possible to communicate to standardized control communications. And these interactions are interfering with the trading results done by the energy and flexibility markets, but they have a higher priority. So this is always the ultima ratio to intervene in the energy and flexibility market results. Now we come to the implementation of the peak platform. This is divided into two phases. The first phase is in the low voltage level, and this is done with the usage of the smart grid laboratory in our campus. So this is a real voltage grid with 12 electrical nodes, where load banks and inverters can simulate household loads and electric vehicle loads, and also PV feeders. And in the second phase, we go from the low voltage up to the middle voltage, and we make a multi-voltage grid simulation. And in this phase, we want to evaluate the scalability of the concept. And yeah, thank you for your attention, and I'm open for your questions.
Thank you very much, Martin. So there is any question from the audience? We have a couple of them. So I'm curious about the agents. So could you tell us a bit more about them? So what they really are and how they work and the difference among them?
Yeah, sure. 1 second, I have talk up. So the software agent or agent in Germany, it's very irritating because if you talk about agents, everyone thinks about spy agents, but in English it's not that big of a deal. So agent is just some software control process which is optimized for one task, and the agent, the properties which defines the agent are the ability to learn and proactivity. So this differs from a normal software process. And if you talk about agent systems, so agent is always used if you want to decentralize a process, and then you talk about agent systems. So it's a so many agents work together. They can proactively work together or not, but the main components of the agent are behavior scheduler, the private message store, and application-dependent resources. And our task in Peak was to implement everything we want an agent to do in these application-dependent resources, so that an agent initializes itself, it registers at the platform, trades its energy, plans its energy. So for each agent, we developed a lot of applicant-dependent resources. And these 4 agent types I already talked about. It's grid agent, market agent, prosumer agent, and platform agent. And we worked with 3 other universities, and each of one university was responsible for 1 agent, and the task for the BOW, the University of Wuppertal, was the grid agent with the grid state forecast and the sensitivity analysis if there's a grid congestion forecasted. And because it's a standardized protocol, the agent communication language, these development can be independent from each other because the format, the communication format, is standardized. So that's the advantage of these implementations. I hope that clears your question.
Yeah, thank you very much. So for me, it's much clearer. So I hope for the audience also. Now another question is about the current situation, of the infrastructure. So how to integrate PIC with the old grids, if the current infrastructure are ready for the integration, because sometimes it can be a bit hard.
Yeah, we can go to this page as example. So our concept or our project is located in the distribution grids, so low voltage and mid voltage. And in these grids, there's another challenge for our research because the availability of sensor data is very limited, especially in low voltage grids. There are a lot of grids with no sensor data, so it's really hard to detect or even forecast grid congestions. But as with the smart meter coming into play, we see a good chance that this data will get better. So we have data to work with and also implement these types of concepts, because we already implemented concepts to be able to do grid state forecast with a low level of data and also with no data, but the deviation gets higher and higher if you have no data available. So you only forecast with standardized load protocol loads, and you can't use the data to increase your the grid state forecast. So it's a challenge. We are working on it, but with smart meter data, we see a good chance that there will be data available even in low voltage distribution grids.
I think also as the main challenge that you have any data in a low voltage grid. So all the providers for low voltage grids are blind in this grid. So if you use smart meter gateway or smart metering, then we have the information about the actual situation in the grid, and then we'll work such a calculating such a model for casting the usage and the consumption of more and more better process, I think. Yes. And I think it's an challenge because all the providers in the low voltage grids are very, how I say, old-fashioned. So So this is not very, very slow digitalization. And it's a deep challenge, I think, that we can use such a technology for calculating things, even with the forecast information.
But
do you think the opportunity of a nationwide rollout of such a network, such a sensor? So we have the new energy Gesetz, Energiengesetz, where all the users of or producers of energy up to 6,000 kilowatt hours will need to implement smart meter gateways, but it's only in the end of the 20s, maybe 28, 30. So there are up to 7 years till we can use it in a wide range. Do you think it will be in some facts earlier to applicate such a technology?
So, colleague of mine did investigation how many smart meter percentage you need to be able to do a good state identification, and his results showed that if you have 30% of the smart meter data implemented into the grid, you have a good enough state, or a good enough great state identification. So you don't need every smart meter data implemented, but enough. And this enough is not similar to each grid, so it's grid specific. And this is also an area we want to investigate further with a research project, how to implement the smart meter data so that you can implement such a concept into real grids, and you have a good data start point and data visibility for your grid. So this is, you can't tell it for every grid, so you need to investigate it for grid specific types. But 30% is for the first part something this is possible in the next years, and yeah, this is a good start point. So you don't need 100% to do that.
Yeah. Fine. Thank you.
No problem.
Thank you, Martin. So, there is any more question? So if there is no more question, I will finish with the session today. So thank you, Ivan, and thank you, Martin, very much for your time and for sharing your knowledge. So we appreciate a lot your participation in our coffee break. This helped us to spread the IoT world. So I hope everybody has enjoyed the talks and has learned something about the smart grid as I have. So if you're interested in more IoT topics, please follow us, follow the IoT Plus network. If you have any question regarding the network, just send us a message. And that is for today. So thank you, Jackie, for your support. And thank you, everybody, for joining us. Have a great afternoon. Ciao.